Hello everyone, this is video 2-8 to be watched on Tuesday, October 11th, on or before that. And tonight's homework is page 12, the whole thing. It's just 2 examples. Okay, so before I jump into these examples on this page, I want to talk to you for a moment about something called local linearity. You don't have to write anything down here, guys. You could just watch. And the idea of local linearity is this. I'm just going to explain it in words. So here's the idea. Any curve, no matter how curvy it is, if you zoom in on it close enough over and over and over, it's going to look like a line. Okay, so right here I've graphed a function. This is y equals 1/4 x squared. Okay, so right there. And what I'm going to do, and you don't have to do this at all, you could just watch, but I'm going to zoom in on a specific point of the graph, and I'm going to zoom in several times, and you're going to see that the curve is going to look like a line. So I'll go zoom, and then I'll zoom in, and so there's the x value, about the x value 2. Okay, so I'll zoom in on the curve around the x value 2. All right, so here I'm zooming in once. Okay, and I'll do it again. So the nice thing about this zoom feature is that the blinky thing, so the center of where you're zooming, it's always going to be, it's going to stay right there. So I don't have to move this again. I'm zooming in for a second time, very close to the point on the graph that has an x value of 2. And you could see it's looking more and more like a line. This is the idea of local linearity. No matter how curvy something is, if you zoom in close enough, it's going to behave like a line. So let me zoom in again for a third time. It's looking more and more linear. Okay, that looks pretty close to a line to me. And guys, let's take a look at the window that my calculator is coming up with each time I zoom in. And if you look here, at the x min and the x max, very, very close to an x value of 2. So yeah. All right, so I just wanted to point that out to you because that concept of local linearity is the basis behind what we're doing today. Okay, here we go. So off to the side, we have this function, f of x, and we have the tangent line, which they are calling L of x. And if you take a look at the graph of f of x and the graph of L of x, for x values, oh, and by the way, this is L of x is the tangent line at the x value a. So for values, for input values very, very close to a, the output values of the line are very, very close to the output values of f of x. All right, so here we go. If f is differentiable at x, which means that it has a derivative, or at a, my bad. If f is differentiable at a, and differentiable just means that you could take its derivative, and some value x is close to a, then the tangent line L of x, and write this in guys, at x equals a, is close to f of x. And you could take a look at the figure there, and this is basically local linearity. If you zoom in over and over at this point here, then pretty soon the function is going to look just like the tangent line. All right, that's the idea of local linearity. And we're going to use that idea to approximate function values. So example number 1, write an equation of the tangent line to f of x equals x cubed at 2, 8. And then after we do that, we're going to use the tangent line to find the approximate values of these numbers here. Okay, guys, so the first thing I'm going to do is I'm going to say to myself, well, if I'm writing the equation of a line, or in this case the tangent line, I need to know the point of tangency, which is 2, 8 right there. So this is the point, I'm going to say POT, which means point of tangency. So I need to know the point of tangency, which I do, and I also need to know the slope of my tangent line. Well, what's another name for the slope of the tangent line? The derivative. So I'm going to go over here, I'm going to say m equals f prime of x. So m equals 3x squared, just using the power rule. So at x equals 2, that would be the x value for the point of tangency, m equals 12. Okay, so right there. So now I'm going to write the equation of my tangent line using the y minus y1 equals m times x minus x1 formula. So y minus 8, that's the y coordinate of the point of tangency, equals m x minus 2. Okay? And I'm just going to add 8 to the other side there, or add 8 to both sides, and then I'm going to replace y with L of x. So L of x equals 12, x minus 2 plus 8. All right? Now, if you left a y there, guys, that's fine. But the reason I put L of x there is because this line is what is called the linear approximation of f for values close to, in this case, 2. All right? So right up here, L of x is the linear approximation of f for values close to a. And guys, the linear approximation is just the tangent line, the equation of the tangent line. All right, so now I'm going to use this tangent line to find approximate values of these numbers here. And I'm going to write it out real nice. Like I'm going to write out the logic of this process. And I would like you to do the same. Alrighty, so I have it written over here. So I'm going to say off to the side. So for this one first, so I'll go like this. I'll go first f of 1.9. All right, and now here's the logic. 1.9 is close to 2. All right, therefore, f of 1.9 is approximately L of 1.9. Okay, so this is the logic right here, guys. For input values very close to 2, the function output, the output of f is going to be very close to the output of the tangent line right there. And then right below, I'm just going to go, so f of 1.9 is approximately, and I already plugged this into my calculator, so I plug in 1.9 into, L of x, and I end up here with 6.8. Alrighty, so there's the first part. Now, second part, okay, I'm going to be very clear about the logic here to my reader. So I'm going to say right here that I'm finding f of 2.01, and then I'm going to use the same logic as I did before. I'm going to say 2.01 is close to 2, therefore, f of 2.01 is approximately L of 2.01, the tangent line at 2. So, and then down here I'll say f of 2.01 is approximately, I got this earlier, 8.12. And I don't know, maybe box those up because that's like what we're finding. Okay, so there's that. Now, down here, we're going to do example number 2. If f is a differentiable function, and differentiable just means you're able to take its derivative. You will see in the future sometimes you can't take the derivative. So if f is a differentiable function, and f of 2 equals 6, and f prime of 2 equals -1/2, find the approximate value of f of 2.1. Now guys, we have no idea what the function f is. So we can't just plug 2.1 into f to find its output. But what we can do with this information here is that we can find the equation of the tangent line, which will give us, we can find the equation of the tangent line at 2. Because here we have, all right, so this would be your x and y coordinate pair. right there. And then, so we know 2, 6 is a point on F. And then furthermore, we know the slope of the tangent line at 2. So we can use the y minus y1 formula, all of that stuff, to find the equation of the tangent line. And then if we know the equation of the tangent line, since 2.1 is very close to 2, we could use the tangent line at 2 to approximate the value. Okay, I hope I'm being clear, guys. If I'm not, we could just talk about it in class. So, alrighty, y minus 6 equals -1/2 x minus 2. Okay? And then I'm just going to add 6 to both sides and then replace y with L of x, which stands for the linear approximation of f at 2 here, because that's the x value that we're approximating at. Okay, and then I'm going to be very clear for my reader, just like I was before. By saying something like this, guys, you're setting up for your reader why you're allowed to approximate like this. You're making it clear to them. So I'm going to say, I'm going to say 2.1 is close to 2. Therefore, f of 2.1 is approximately L of 2.1. And so f of 2.1 is approximately, so I take 2.1, I plug it into L. I already did this earlier, and I got 5.95. Okay, guys, so there's that. And the homework is page 12, the whole thing. I hope that was clear. I felt like I was, fumbling my words a lot. If you have any questions at all, please just email me. Okay, see you soon.